So the next talk is Petuum, a new platform for distributed machine learning on big data. And the presenter is Qirong Ho from the Institute of Infocom Research.
Okay, testing. Looks like this works. All right, good afternoon to everyone. I'm Qirong, as been introduced, and I'm here to talk about the Petuum platform for distributed machine learning. So I think the current setting we all face in the big data world is that there's a wide variety of distributed programming tools. And this is sometimes jokingly referred to in the Hadoop world as the zoo of things. So I think from more data mining or ML perspective, one might want to ask, what's the connection between all these tools? Is there a set of general principles that underlies them? How has that influenced the design of systems for distributed machine learning and data mining problems? So I think many of us have some ideal traits we desire of a large-scale machine learning and data mining system. We obviously want massive data scale. For those of us that are doing very large modeling problems, such as, say, certain matrix factorization, collaborative filtering, or deep learning problems, we want to be able to accommodate billions or even trillions of variables. At the same time, we'd like to support a variety of modern optimization as well as probabilistic methods, as has been covered earlier in this session. Now, the current practices are maybe for massive data scale, you might use, say, the Hadoop ecosystem to deal with storage and processing of it. For dealing with very large models, it's pretty common to implement a bespoke or custom model for each kind of application you want to do. And as for a broad spot of things, I think everyone gravitates to a certain favorite tool they have, one or another, use a different program for each platform. So I think to unify all of these ideas, we could take the view that most of these problems are simply iterative-convergent problems of the following form. It's a kind of maximization over some kind of loss function over data and parameters, and perhaps some kind of regularization or prior function in the, say, probabilistic setting over the parameters themselves. Generally, almost all the problems we look at in data mining and machine learning are iterative in nature. That is to say, you do a for loop over t equals 1 to t. You might do something at the start, the end of the block, but there's a key update step where you take the parameter and update it via some change. Maybe that's additive. More generally, it might be some kind of aggregation, transformation function, perhaps like a proximal step or proximal operator. Okay. Given this, why is this view important? So we want to look at a broad class of problems, and we want to identify the principles that are common to all of them so as to build a general purpose system that shows speed up and shows increased efficiency for many of the problems you want to write on it. And the view matters because an ML or data mining problem is usually optimization or perhaps Markov chain Monte Carlo-centric and iterative-convergent, as opposed to, say, a more classical CS algorithm, which is operation-centric or deterministic. A good example of this is the classic merge sort algorithm, where if you have a single error during the sorting process, let's say that parallel worker over there puts 5 before 2, that error is going to propagate through the algorithm, and the final answer is incorrect. But many of us, we do know that for many of these iterative convergent algorithms, minor errors in the model state are actually kind of similar in effect to random noise. This is actually the reason why stochastic algorithms, which are one of the popular methods today, are so effective, because the randomization of a data points is treated as some form of stochastic noise. So one intuition in designing a system is to take advantage of this self-correcting property to improve system design and to allow for the use of flexible communication strategies that might deviate from, say, the classical bulk synchronized parallel methods. Right? The second insight we want to look at systematically is that many of these algorithms have some form of structure. Very briefly, it's saying that model parameters are not independent in general. And for certain algorithms, it's possible to group the parameters into certain blocks, where the parameters in blocks A and B are independent of each other. Inside a block, you'd update them sequentially. Between blocks, we update them in parallel. A third intuition is that many of these algorithms can exhibit non-uniform parameter convergence, and that some model parameters may converge much faster than others. So, for example, empirically, let's say you're doing a sparse regression on over 100 billion parameters. In general, you'll find that 85% of the parameters will converge, say, within 5 iterations. However, the remaining 15% may require up to 100 or more iterations, and you'd want to be able to prioritize the CPU on some of these slower parameters so that they all converge at about the same time, and basically, it's a form of load balancing. All right, so given these 3 intuitions, which are common to a large class of machine learning and data mining problems, how does one build a system about it? Before we talk about that, we need to speak a bit about, say, parallelization strategies for algorithms. So in general, there are 2 broad classes of strategies. One are the data parallel strategies, of which stochastic methods are a prime example, where you split the data over you split the responsibility for working the data over many workers. That doesn't necessarily mean you partition the data, but just means that the responsibility is divided across data. Then there are the model-parallel strategies, such as the coordinate descent family of algorithms, or even PageRank is a classic example of this, where you split the responsibility over the parameter space. So that's to say, some workers will get parameters 1, 2, and 3, other workers 4, 5, 6, and so on. So these are 2 broad themes that are seen in many parallelization strategies, and some methods are even a combination of both. So the main difference between data and model parallelism is that there's generally an assumption in data parallelism that the data points are IID. Almost all models have the assumption that these data points are drawn from the same distribution independently. Whereas in model parallelism, the model parameters are not exactly independent of each other. A good example of this is in linear regression methods, where in the coordinate descent literature, you find that the empirical correlation between feature columns actually affects the quality of convergence. Graphical models are another example. It's well known that if you want to do Gibbs sampling in parallel, you have to make sure the Markov blankets don't overlap for the different variables. Okay. So the focus of the Petuum system is to find systematic ways to improve both data and model parallel algorithms based on the 3 intuitions I described earlier. So one of those systems performs what is called bounded-async consistency, which is a way of allowing different workers in a distributed system to communicate with each other in a way that's asynchronous, which means that some updates can arrive late, but the delay is bounded. The idea is that you want to exploit this self-healing or robustness to noise property to communicate in an opportunistic manner, but with a certain amount of guarantee that is enforced by the fact that there's a staleness bound on it. The other type of system in Petuum relies on something we're calling structure-aware parallelization, which is to use the block structures that I talked about, as well as the uneven convergence, to schedule these model parameters for updates in a different but more efficient manner. The point of bounded asynchronous consistency is to improve the iteration throughput, the rate at which the system executes machine learning updates, without compromising on the iteration quality. And the point of structure-aware parallelization is to improve the iteration quality without sacrificing iteration throughput. And I'll get to some empirical results in a minute or two. Okay. So for the bounded asynchronous consistency, we're calling the system boson, which is actually a key value storage for model parameters that provides asynchronous-like access and has bounded delay via a bridging model we call eager-stale synchronous parallel. A bridging model, one example of a classic bridging model is the bulk-synchronous parallel model. A bridging model is a model that specifies how a program should do its computation and its communication, and it's not actually a system, but simply a way of thinking about programs. So under this bounded asynchronous ESSP model, the general idea is that threads or workers in general, will be allowed to deviate from each other in iteration count, but only up to a certain limit. For example, if you set that limit to 3, then workers are not allowed to deviate by more than 3 iterations. And the idea is this controls the amount of error or noise in the problem that still allows the problem to converge, while allowing the system some opportunities to schedule communication in an efficient way. The other idea, structure-aware parallelization, is a scheduler system that does 2 things. The first thing is it avoids concurrent updates on parameters that are not independent. For example, highly correlated features in a coordinate descent problem, or different variables in a graphical model that are adjacent to each other and linked. So this is important for avoiding problem divergence or low quality of the solution. The second thing it does is to prioritize computation on the slower to converge parameters, thus achieving a form of load balancing. Okay. So in terms of technical implementation, the Bose system, which is the bounded asynchronous parallel system, allows the model updates to be pushed out eagerly, which is to say we push updates to the machines before it's required by the workers. This lowers the average variance and mean of the staleness parameter, which is the gap between each worker's view of the parameters. And we'll see that there's some theory analysis that shows that this will improve the quality of the solution. Then there are some other features that we're working on that are still in publication, which is prioritize communication strategies to further optimize the bandwidth usage, as well as automatic, what we call adder revision style step size tuning for improved convergence. These are done on the system itself so that the user doesn't have to program it. On the other side, the structure-aware parallelization is handled by a system we call STRADS, which performs this, what we're calling prioritization with dependency analysis. So the prioritization is simply doing those parameters that are slower to converge more often, and it means fewer parameters to be analyzed for dependencies. The idea is that if you have 1 billion parameters, and you choose 100 of them to do in parallel, you only have to analyze the dependencies between 100 of them instead of building a full graph of dependencies between the 100 billion parameters. So this allows the dependency analysis to proceed faster. And we've also got some upcoming research on this involving pipelining, which is to overlap many small parameter batches to eliminate the synchronization barrier, as well as communication topologies to further reduce the network traffic. So that's on the technical side of things. On the overall structure for Petuum program is roughly a 3-phase program we're calling schedule, push, and pull. Schedule is the function in which parameter prioritization happens, and it's where we also group these parameters into blocks of non-dependent parameters for dispatch to workers. Push and pull are similar to a MapReduce system, where push is roughly equivalent to map, and pull is roughly equivalent to reduce. The key difference between our system and MapReduce-like systems is that the model parameters are made globally accessible through the Boson key value interface, which employs the bounded asynchronous consistency models for basically asynchronous-like performance and speed up. Right. So let's talk about efficiency of these systems. One key point we are trying to emphasize with Petuum is that it allows a wide class of machine learning problems to be more efficient in terms of speed. And we're going to demonstrate this with the collaborative filtering problem, otherwise known as matrix factorization. So on about 64 machines with 330 gigabytes of data, what we see is that the Boson bounded asynchronous parallel system, if you look at the graph on the left side, that's the objective versus iteration count graph. And what this is trying to show is that for the same number of iterations, the progress, the convergence, is roughly the same, meaning that the cost of applying this bounded asynchronous parallelism is not much higher than, say, totally synchronous excess. However, if you look at the right, the iteration throughput is improved. So what's happening here is that if you take the product of these two graphs, that's going to be the real-time convergence rate, or the objective value versus time. So in this case, just bounded asynchronous parallel alone is improving the convergence rate by about 33%, but we can go a little further than that. When we employ prioritized communications and server-controlled step size, you can actually dramatically reduce that curve even further, as well as improve the objective quality. So what we're building here is a key value store that employs bounded asynchronous communications to increase the iteration throughput, as well as some work on prioritization on the communication side, as well as step size control to further increase the quality of each iteration. On the other side, the STRADS structure-aware parallelization system, we've done some work on sparse logistic regression with 16 machines and about 150 gigabytes of data. But the key difference in our setting is that nearby features in the problem are highly correlated. For example, due to feature engineering, say you've got an autoregressive model, you're putting features for 5 minutes behind, 10 minutes behind, 1 hour behind. This causes a lot of correlation in the problem. What happens when you perform a naive coordinate descent algorithm is that the right graph, that's the iteration quality versus the quality versus each iteration. You'll see a very, very slow convergence rate due to the high correlation in the problem. Applying the strat system allows that curve to be a lot steeper. Basically, it's making a lot more progress for each iteration without compromising on iteration throughput, which is the left graph. Right? So you can see that the gap between the left graph, the 2 lines, there's a little bit of penalty for applying the dependency checking and prioritization, but it's very small. Take the product of these 2 graphs, and you essentially get a real-time convergence curve that is a dramatically improved system. The other point about Petuum is that we also focus on efficiency and problem size as a distributed system. So what we're trying to show is that large models, even on smaller clusters, are actually possible to run. For example, say a very high-rank matrix factorization or a 200+ billion parameter latent array allocation. I think the reasons for these improved efficiency in size and speed, the speed I talked about already. Bounded-Async Consistency allows for more iterations per second without compromising model quality, and structure-aware parallelization allows more progress per iteration without compromising iteration throughput. You take the product of 2, that's more progress you get per second, which is speed. And now, why are bigger problem sizes possible? I think the answer here is that with the ML sort of self-healing property in these iterative convergent problems, certain kind of operational correctness logic, such as exact backups or, say, exact lineage tracking is not necessary. So you have data structures that are more lightweight, approximate recovery is sufficient for making these problems work, and you allow basically larger problem sizes on a given amount of memory. Okay. I want to briefly finish off by talking about some theoretical bounds that actually analyze the impact of bounded asynchronous consistency and structure-aware parallelization. So very briefly, for bounded asynchronous parallelization, the quantities you're worried about are the staleness, or basically the deviation between different workers. That has a limit imposed by the system, an upper limit. It also has an average, and it has a variance. These 3 quantities are essential for bounding the convergence of the problem, and what you can generally show is lower average, mean, and maximum improve the convergence dramatically, and that's exactly what the system is trying to do here. The second theorem I want to briefly cover is the structure-aware parallelization to explain why we see the sharp convergence curve. And that's because it's actually equivalent to a sort of ideal scheduling where you form a graph over all the parameters and only do subsets of parameters in parallel that are independent, right? So that's briefly, the analysis briefly involves a spectral radius of the problem and showing that the term in the red box over there is basically negligible, right? There's also an idealness guarantee here in the sense that if you could have an oracle that selected the ideal trajectory for these problems and compared it to the trajectory that's actually employed by the scheduling, you'll find that the difference shrinks with iteration count at a quadratic rate, meaning that after a reasonable number of iterations, the difference is negligible and you have as fast performance as possible. I'd like to end that by saying that we've implemented a number of algorithms on this platform to show that it's actually generally applicable. Some newly added features include HDFS and YARN support, distributed GPU supports for CNN, and a Java version of the bounded-async key-value store called JBoson. We're looking to grow this project, so if anyone is interested in collaborating with us, we'd be very happy to hear about that. And I want to quickly acknowledge the funding sources, which we've got quite a few of here, as well as our systems collaborators at Carnegie Mellon University, Garth Gibson, Greg Ganger, Phil Gibbons, and Jim Sipa. That's the end of my talk. Thank you.
One question? Oh.
Yes.
So you commented that you could detect things that were largely independent of each other and use them to schedule parallel updates. I wonder whether you've thought at all about the converse detecting things that are very closely related and applying block coordinate descent rather than individual coordinate descent type of updates?
Actually, that's in fact what we're doing. So they're both part of the same process. Finding out what's independent and finding what should be scheduled together. So the independent things are done in parallel, and the block coordinate descent is applied within a block. So you actually find blocks that are pairwise independent between the blocks. Within the block, they may be highly correlated, and you do those in sequence on one worker. But different blocks are on different workers. So there's both a sequential and parallel in the block coordinate descent sense, except we're sort of doing it dynamically at a very fine-grained scale, which is made possible by efficient pipelining of the problem from the system's perspective.
Thank you. Thank you very much.